Turn on any modern metallurgy lecture, and you will hear the same message: high performance, steel demands, controlled atmospheres, digital thermocouples, proprietary alloys, and a supply chain that stretches across continents. The implication is clear. Without industrial infrastructure, you are left with crude iron and guesswork. That narrative collapses the moment you study how pre-industrial smiths produced blades, tools, and springs that powered civilizations. In a true grid-down scenario, the billion-dollar laboratory is useless if it cannot function without power. What remains is fire, carbon, clay, and knowledge. Ancient chemistry was not primitive. It was focused, efficient, and entirely self-contained. Super, the final siren. Performance steel begins with carbon control, not computer control. Modern alloy production certainly achieves extraordinary consistency, but at its core, steel performance still depends on carbon content and heat treatment. Raise carbon levels, harden through quenching, and reduce brittleness through tempering. That formula predates industrialization by centuries. Ancient smiths increased carbon content through carburization. They took low-carbon iron or mild steel and packed it in sealed containers with carbon-rich materials. Crushed animal bones, reduced to bone charcoal, were among the most effective sources. When heated to high temperatures in a low-oxygen environment, carbon migrated into the metal's outer layers. The result was case-hardened steel, capable of holding a sharp edge. You can replicate this today without sensors. Shape your steel blank to near final form. Clean it thoroughly to remove scale and oils. Place it inside a clay-sealed container packed tightly with powdered charcoal and crushed bone charcoal. Seal every seam with wet clay to prevent oxygen intrusion. The objective is simple: allow heat in, keep oxygen out. The sealed clay furnace is, well, the real laboratory. The furnace does not need digital displays to be effective. A clay furnace built from refractory earth and sand can reach critical temperatures when supplied with steady airflow. A hand-powered bellows, or even a well-designed natural draft chimney, provides sufficient oxygen to sustain intense combustion in the outer fire chamber. Place the sealed container within the hottest zone of the furnace. Maintain a bright orange heat for several hours, depending on the thickness of the steel. Historically, smiths judged temperature by colour and spark behaviour. A bright orange glow in low light conditions generally indicates the range necessary for carbon diffusion. The clay seal performs two functions. It prevents oxygen from burning away the carbon source, and it ensures that carbon remains concentrated around the steel surface. This creates a controlled microenvironment without laboratory instrumentation. It is chemistry governed by containment rather than electronics. Crushed animal bones are not superstition, but a mineral advantage. Bone charcoal differs from wood charcoal in composition. Bones contain calcium phosphate and trace minerals that influence surface reactions during carburization. When reduced properly in a low-oxygen burn, bones become porous carbon structures capable of contributing to deeper and more consistent case hardening. To prepare bone charcoal, clean the bones thoroughly and allow them to dry completely. Place them in a sealed metal container with a small vent hole to release gases. Heat the container in a fire until smoke production subsides. Once cooled, the bones will be brittle and blackened. Crush them into fine granules. mixed with hardwood charcoal powder. This material surrounds the steel evenly. During high heat exposure, carbon atoms migrate into the steel's surface layers. This is not folklore. It is diffusion driven by temperature and concentration gradients. Heat treatment, really determines whether the process succeeds or fails. After carburization, the steel must be hardened. Remove it from the container and reheat it in the furnace to critical temperature where it becomes non-magnetic. At this point, quench it in oil to lock the carbon in a hardened crystalline structure. Oil reduces shock compared to water, minimizing cracks. The blade will now be hard, but honestly quite brittle. Tempering follows. Reheat gently to a lower temperature, traditionally judged by oxide color on polished steel. A light straw hue often indicates a balance between hardness and toughness for cutting tools. You can test the result with a simple file test. A properly hardened surface will resist a file bite. For a more practical evaluation, cut rope or shave hardwood curls. Performance in real material is in the end the ultimate measure. Modern alloys, they excel in complexity, but simplicity wins in isolation. Industrial alloys offer corrosion resistance, extreme tensile strength, and engineered uniformity. Yet, in a total grid-down scenario, those alloys cannot be repaired or reproduced without specialized facilities. The ancient method does not compete on laboratory precision. It competes on independence. A case-hardened blade made through bone charcoal carburization can serve for years with proper maintenance. If damaged, it can be reforged and rehardened using the same process. The materials required are locally obtainable: clay, wood, animal bone, and basic steel stock. The key lesson here is resilience. Performance is not defined only by maximum tensile numbers. It is defined by reproducibility under constrained conditions. Applying this knowledge really begins with small controlled experiments. If you want to test the principle yourself, begin with simple steel rods rather than full blades. Carburize them in sealed clay containers for varying durations. Cut the rods in half after hardening and examine the cross-section. You will see a darker outer layer where carbon penetrated. This visible case depth teaches more than theory ever will. Gradually increase complexity. Shape a small utility knife. Carburize, harden, temper and evaluate edge retention. Keep notes on heat duration and quench medium. This iterative approach mirrors how historic craftsmen refined their technique long before metallurgical textbooks existed. The grid does not define capability. Knowledge does. Modern metallurgists are correct that the industry produces remarkable steel, but they are wrong to imply that high-performance material cannot exist without it. The sealed clay furnace and crushed bone method prove that advanced results can arise from elemental processes. In a world increasingly dependent on fragile systems, understanding these principles restores agency. Fire, carbon containment, and controlled cooling remain powerful tools. The laboratory may go dark, the furnace can still burn. If you value serious historical insight, practical metallurgy, and real self-reliance skills, subscribe to the channel and share this episode with fellow history enthusiasts and preparedness-minded viewers. The past still holds solutions powerful enough to outlast modern infrastructure.